So now we are going with Professor Pablo Otero. He's associated professor from University of Malaga in Malaga, Spain. His PhD in telecommunications from Communication Engineering School. His research interests include antennas, transducers, and underwater communication. In the last 25 years, he was involved in several projects about communications and radar system, worked with corporations like Standard Electrica, Navantia, Telefonica, and several universities such as École Polytechnique Federal of Lausanne, University of Sevilla, and University of Malaga as well. Professor Pablo Otero, you're welcome, please.
Good morning, everybody. First thing I want to say is I'm very grateful to Navantia Monodon for inviting me. Thank you very much. It's an important opportunity to show our work. As Tamara said, I'm, well...
This one.
Ah, okay.
This one.
Excuse me. Excuse me.
No problem.
Thank you. These are the contents of my presentation. I will, first of all, present my institution, and then I will go into the main subject of my talk. Please allow me to do this. I come from the University of Malaga. Malaga is an important city in Spain. It can be fourth to sixth. That depends on how you count or how you measure importance. This is in the Mediterranean coast of Spain. You can see it there for people who don't know.
Is that working?
No, it's okay. It's okay. You know, sometimes the mechanical things are better, you know. This is Malaga, in the Mediterranean coast. Excuse me. It's okay, excuse me. You know? The University of Malaga is a medium to large size university in Spain. We have over 38,000 students. We have a huge offer of different subjects, and we have, well, common infrastructure of other universities. And this is my school, the Telecommunication Engineering School. Well, this is not my team. This is just a picture that I took, not me, because I'm on the picture, that we took one day after an international meeting, but I wanted you to see the entrance. And we offer the three common levels of university studies. We have a bachelor's curriculum with five majors, 4 master's curricula, one leading to become a professional engineer. And also we have a doctoral program, but doctoral programs are centralized by the doctoral school, which is a virtual faculty of the university. Okay. I'm the head of the Institute of Oceanic Engineering Research. In Spain, university institutes have 3 functions. They are research, of course, but also transfer. Research results transfer to industry, and also training. From the institute, not from the school, we teach courses on masters and doctoral graduate courses. Okay. This is the institute. It is a young institute. It started in 2019, and we gathered all the engineering activities at the University of Malaga that were involved with oceans and the seas. And we are 5 groups inside the institute. One is works in materials. We have 2 scientist groups, algebra and oceanography, and we had the strongest part of the group is signals and communications and microelectronics. And we work together with 2 groups from the University of Cádiz, but from the administrative point of view, they are not members of the institute, but is the Naval Engineering School of the University of Cádiz and the Coastal Engineering Department also. Now, let's go to the main point of my talk. underwater communications. I had prepared this slide, but I think the best presentation has been done by Professor Sousa, explaining why communications are needed. All of you can easily understand. All of you, or all of us, we have a device like this one in our pocket. This is a computer with incredible and awesome computation capacity that we couldn't imagine 20 years ago. But if you remove the communications capability of this device, this is almost nothing. No, it's like a ship without a propeller. No, for you, most of you are naval engineers. This one, I think, it was published. This was when the Nord Stream attack, and that one is a picture of a deployment of an underwater submarine cable. And there is a journalist in Spain who is an expert in geopolitics, is Mr. Enrique Juliana, who 2 or 3 months ago, he's mentioned in his article that what would happen if one communication cable was cut in the sea, and that can be really, really bad for our way of life. And that happened. Last Sunday, on the Spanish newspapers, we read that a communication cable from Germany to Denmark, and vice versa, of course, was cut. They said it was an accident, but who knows? They don't know. At least we don't know enough information about that. This is a very naive slide, but I think it presents very well the scenario of the communications, of the underwater communication. We have drones, we have maybe onshore infrastructures that cannot be only gas pipes or oil pipes, that can be also mining. And we have the need to communicate all those vehicles among them, and also with the external world. This is where we have to work. Okay. When we talk about underwater communication, we say, of course, wireless. We are not thinking on drones with a cable. You know very well the main two problems underwater is there is nowhere to breathe, and there is no electrical outlet to plug our devices. What are the options? What are the options to have underwater communications? We considered 3 options: radio frequency, like our phones, optical, and acoustic waves. RF, electromagnetic propagation in the salted water is very short. The range, we are talking about centimeters, maybe a few meters, depending on the frequency. That makes no sense to communicate drones. Okay, and the optical, maybe the range is larger, but the problem is aiming the beam of the optical devices. So we went to acoustic waves. Well, not me, but maybe researchers before me, and that is what we are doing. What is the situation for underwater acoustics? The aim of my talk was what can we expect from underwater communication, and why? This is when I was invited, I say, what can be of interest for people who are not telecommunication engineers? And I thought, okay, what I can tell them is what they can expect from communications, and if possible, why, because knowing why helps you to solve the problems. Okay, this is the situation. We have computers with capacities is incredible, but in between the channel is like a path in the mountains. It's like trying to drive a Ferrari. We have the Ferrari, we have an F1 vehicle, but we have to go through a very hostile, harsh path. Okay, so what we need is a good four-wheel drive and very robust. And the reason, as I tell you, is the channel. The acoustic channel is the worst channel we can imagine. Bandwidth very narrow, attenuation very high, noise very high, multipath and fading unbearable. We cannot take that, and it is time variant, which is well, for communication people, this is a very bad thing to have a variant channel. Now imagine that you are driving a car and suddenly the turn, instead of being on the right, is on the left and you didn't expect it. What changes with time? Propagation velocity with time and space, and that results in a very high dispersion. Dispersion is not easy, as a concept is not easy to explain, but the results of dispersion is that it distorts the information that you are trying to bring from a transmitter to a receiver. So the net capacity of the channel is very low, and this, when you are trying to do drones on big systems, you need to be aware of that, okay? So what we are doing about that? Okay, I'm going to go through those characteristics. This is attenuation to give an idea of figures. If we go here to 10 dBs per kilometer, these are dBs per kilometer, it's a 10 kilohertz. At 10 kilohertz, if we send a signal at 10 kilohertz, 1 kilometer far, we have lost 90% of the power just because of water absorption. In wave propagation, there are other attenuations, but just in water absorption, we have lost 90% of the power. That makes that is the reason of the very low one of the reasons of the very low bandwidth. Okay, excuse me. We developed several propagation models to analyze what is going on, and we realized that a second big problem is multipath. Multipath is energy arriving to the receiver from through different paths. Okay, you can see this is the effect of multipath. There are regions where you don't receive anything. There are regions where you receive a lot of or even a little bit more power than if it was in open space. No? And on the left side, these are the results that shows fading. Fading is suddenly you don't receive almost any power on your receiver, and that makes that the communication is interrupted. And that changes very, very quickly. You see, you are moving in distance, and you are moving, and you are receiving, and suddenly you don't receive. Okay. Noise. We have so many. We think that what is underwater that can generate noise, but there are many things there that can generate noise. You have a picture there. We have submarines. I mean, engines, propellers. We have marine life. We have human activity. We have the sound of ships, and you know much better than I do. The ships traffic in the world is increasing and increasing and increasing. We have every time we have more ship noise in the sea. Okay, and we have also bubbles. We have surface waves or the wind on the surface of the sea. A lot of noise. Dispersion. This is what I told you, that the result of dispersion is that the signal at the receiver is distorted, so maybe you cannot recognize what is like if you are speaking and suddenly something distorts what you are hearing, and you cannot understand what the speaker is saying. There is a key. We have two problems here. Multipath. Multipath is, as I said, the energy coming from different paths or through different paths and moving scatterers. Multipath, what it does is, there is a key point there. You see, I put it in red. The propagation velocity of sound in the sea is very, very low compared to electromagnetics in air. It's around 1,500 meters per second. So that makes that the propagation time, the time that needs a signal to go from the transmitter to the receiver, it is comparable to the transmission time. And the result of this is that capacity is still lower. It's capacity in terms of information that it can travel through the channel. Okay. But not only that, is that in terms of multipath, if I imagine that you are transmitting 1 bit, 1 bit is like 1 impulse. You receive that impulse, okay? But you receive a copy of that impulse because of multipath. And due to that very small speed, that can be almost 10%. This is an example, but with realistic figures. That can be 10% of the duration of the bit. That makes a big problem to detect it or to recognize what it is. And the second problem is what we call Doppler spread. The frequency where the information is modulated will spread over the frequency axis. And the reason is, again, that very small c, okay, compare. So this term that changes the transmitted frequency to the received frequency, that term that in electromagnetics here is around 10 to the minus 8, in acoustic is 5 orders of magnitude bigger. And that makes, again, very difficult to detect the information that you receive, okay? Well, I think I put too many slides. What is the knowledge then about propagation? I think physical models, they are very interesting. We can publish articles in the technical journals, but they are not useful for planning underwater links. So finally, we go to statistics. And we still have very few statistics about sound propagation or ultrasonic propagation underwater. Okay, maybe the big countries, their defense forces, they have those knowledge, but in the literature we have very few. I think we still need to work on that. Networks. I will talk about networks a little bit later. Regulation. There is no legal regulation about underwater communication similar to what we have in electromagnetics. In electromagnetics, we have the International Telecommunication Unit. They fix rules for the different countries to use the radio frequency spectrum. That is not true underwater, or not yet. Okay? But we have a couple of standards, and they are NATO standards. The first one is ANEP, ANEP 85. It deals with analog communications, and its purpose was emergency in submarines. Okay, but now talking about what we are talking today, we have the second standard that is called JANOS, and is standard ANEP 87, and the version 2. It was published in February this same year, okay? And this, I want to mention here that this standard uses a transmission technique that we call frequency hopped binary frequency shift gain. Is FHBFSK, okay? And the reason of using this is a very simple, in terms of communication, this is a very simple transmission modulation. And the reason that they wrote, this is literal from the standard, is its robustness in the harsh underwater acoustic propagation environment and simplicity of implementation. I think this is important. And a second sentence that is in the standard is, it is used in at least 2 leading commercial product modems. So there are at least 2 companies who already have those devices in their catalog. Okay. We have explored, I think, all transmission techniques, very sophisticated transmission techniques that had been used in radio frequency have been explored for the underwater. And the conclusion, I think all the experts that I talked with, they mentioned the same thing. Let's go for a robust and simple thing, because anyway the channel is so bad that what to do. This is the last line. The common feeling is that a simple and robust modulation performs better in the harsh environment. Okay. Transceivers. What are the transceivers in underwater communications? have two parts, the electronics and the transducer. Okay? This is a picture of one, the electronics in OEM configuration that can be integrated with other electronics. There on the left, it is encapsulated in the cylinder. And then the hydrophone, this is the second part, this hydrophone, or that one on the left part of the cylinder. That is the hydrophone. The hydrophone plays the same role that an antenna in electromagnetic communications. It is, but there is a difference. It is a transducer that changes the nature of energy from electric to acoustic. Okay, and normally they are done. They use the piezoelectric effect, and the main problem with those things is that they are very, very difficult to do impedance matching. Okay, that is an electrical concept. Maybe it's not. This is not the place. The good thing is that antenna theory, developed in the 40s, in the 50s of the last century, can be directly applicable to arrays of hydrophones to obtain the beams almost with different patterns. Okay. What is available in the market? There are several companies. I listed, I wrote there several of them. They are written in the alphabetical order. I have no interest in any of them. I'm just a modest university professor. But you have Evologics, Convert, Linkwest, very, very renowned companies that already have off-the-shelf products that you can use and integrate in your systems. Typical carrier frequency. That doesn't mean that the figures, the real figures, will be there. Maybe they are outside those ranges, but this is typical. Carrier frequencies, you see, 10 kilohertz to 60 kilohertz. There is not much bandwidth there. Range, 1,000, 6,000 meters. We have to pay attention to something. Sometimes there is a company that says, I have a modem that with a range of 6,000 meters, and it has a bit rate of 10 kilobits per second. Yes, it is true, but when it works at 10 kilobit per second, the range is only 1,000 meters, not 6,000 meters. There is a trade-off between power consumption, that means autonomy, and remember, we don't have plugs down there, and range and bit rate. Okay. You can increase one, but then you decrease the other two. Okay. Networks. This is very important, and I think Professor Sousa explained it very well. When you have different drones moving around and they need to communicate one each other. Ranges are so short that we need to talk about relay communications. I mean, you cannot, with a range of 2,000 meters, you cannot reach where you want to reach. So we need to do relay-based topologies, network topologies. If the nodes are fixed, this is easier. In that case, the best technique is TDMA, time division multiple access, because this is the optimal use of the spectrum. Okay, but when they are moving, that changes, and we need a communication strategy, and the topology will be dynamic. And the problem, what happens with this is that handshake between nodes can block off the communications. You know, when you are moving and you need to know where is the best path from one point. For instance, this is one of our works that we did a cluster system. We have head clusters. The red dots are head clusters. Several drones or several mobile nodes can be in the range of this cluster head, and then but they also move, and so you need to find the best path from this cluster head to maybe a surface vessel, and this is moving, and you need to establish the path. You need to transmit information that is not payload. This is just to organize the network. And the problem is we are scared about the point that just making the handshake can block the network. This is a very, very important point to take into account, okay? And also, it was in Professor Sousa's presentation, is the concept of mule. Maybe we need to go back to the past. And I remember, and we talk about mule drones, just to carry information from one point to another. The mission of that drone is to carry information from one point to another. And that remember me when I was a kid and I read that novel by Jules Verne. It's Miguel, well, in Spanish, Michel Strogoff in French. And what happened? Someone cut the telegraphic lines and very, very old. You know, the first telegraphic cable between Europe and America was deployed in the 50s, but not in the 50s of the 20th century, but in the 50s of the 18th century. It's incredible. For me, it's incredible. Okay, someone cut the telegraph lines. What did the Tsar? He sent a courier on a horse, riding a horse. And maybe we need to go back to this kind of thinking for mobile networks. And the point here is AUVs, underwater positioning. I didn't mention in one of my slides, underwater positioning needs underwater communications, and underwater communications seem to be complementary and inseparable technologies. We cannot imagine one of them without the other. This is one example of application. This is a recent project that we did. We developed a system so that an underwater vehicle can know where it is, which so far it is not, up to my knowledge, that is not very easy to do. And what we did is we developed a kind of a GNSS repeater. So any number of underwater vehicles who are in the range of 4 of those 4 buoys that can be drifting, we don't need to fix those buoys, can calculate its position. Okay. This is the key issues. Well, this is a picture when these are the yellow buoys are our GPS. We use GPS signals, our GPS repeaters, and this is a small, very, very small drone. This is amateur drone that we use to demonstrate the concept that we were developing. But now, let me conclude my presentation with several personal impressions. Okay. First, there is still room to improve underwater communication, acoustic communications in terms of transmission technologies. But in my humble opinion, there is a little room for that. Okay, those companies will do better, but maybe not in capacity. They will do better in other aspects. Okay, maybe prices. This is maybe 100 euros, 200 euros. I bought several modems, simple modems, and I had to pay almost 6,000 euros a piece. So it's a huge difference. But when the market will be not mass market, because underwater will never be a mass market, but much larger market than it is now, I guess prices will go down, okay? But the challenges, for me, the challenges now are routing protocols that will make possible that the network will not collapse, just trying to establish paths from the whatever is underwater to the surface. A very important point is covert communications. This is, I think, from the point of view of defense, that will be very, very important. And the third point, that we need to do something that will be even a standard for a European standard or a world standard of underwater positioning that we don't have as we have GPS, Galileo, etc. And that's all. That is my email address, in case you need. It's good. Thank you. Thank you very much.
So much. Thank you so much, Professor. Question from the audience? Yes, please, go ahead.
Good morning, Professor. Really nice presentation. I have ask a question related to the future of the communications underwater. So companies like you mentioned have tried to improve communication based on acoustic principle. But my question is, how you see the future of these communications, of this technology, or soon we will see a change on these trends for communications?
Also, Professor Sousa did, and I fully agree with him. I cannot see the future. Okay? If I was able to do it, who knows? I will play lottery or invest in the stock market. Are we going to live underwater? I don't know. But we are going to use resources. So that will, I think the market on underwater electronics will develop a lot in the next 10 years. A lot. Okay. Also, the main point here is, well, the word is there is for a different reason, but the word is there is we need to keep the ocean health. We are all of us agree with that. And that will need a lot of monitoring and maybe actions. And you cannot imagine those things without communication. It's like our life today is communications is not the important thing, but this is one of the most important tools for the way we live. Okay. I don't know if I have answered your question.
Please, go ahead, please. The mic.
I think. Yes. Thank you, because it was really interesting, the presentation. I would like to ask if also is a challenge in the acoustic communications security, to secure the communications, because also is bandwidth consuming. I don't know if it's also needed to standardize that and so on.
Thank you. I think I mentioned it one of the last, my personal points of view. The second one was what they called covert communications. That means that you cannot realize that someone is communicating using acoustic waves. This is one strategy, of course. But there is the classical one that is what we call steganography, and the other one is using encryption, cryptology. Okay. I think related to defense, that will receive a strong impulse in the next years. Okay.
Yes,
We have those two strategies, and I know very leader research groups are working on that. Okay.
So you have pointed out something important, in my opinion, to go to covert communications, not only in defense, because I would say also it may also be important in the civilian sector. Mm-hmm. Do you envisage any way to get to make underwater communications covered?
I think we will see it. I'm confident of that. Okay, but now I have a more philosophical idea about you know, I have friends that don't use WhatsApp. They say, I don't want I don't know, people up there to know what I'm doing, what I'm thinking, what I'm reading. And I said, you know, the best, I don't worry about that, because nobody is interested in Pablo Otero. You know, I am a little ant in this world, you know. And, you know, maybe it will be secure communications, covered steganography and cryptography will be needed in the civil Okay, that is a kind maybe of industrial copying, no? One industry from another, maybe that one.
Yeah, well, what is really, at least in defense, when you are communicating, you are located, directly located. They know where you are, and that's important in defense, that they don't know where you are. So, for instance, you can in the aerial communications, you can use, for instance, direct sequence spread spectrum, so you can communicate below the noise level, and you cannot be detected.
You are fully right. You are fully right. But I remember because I used to work in Navantia in the past, and I was involved in these problems, and also from my engineer. I'm now a quite old engineer. Many times I receive questions from former students and things like this, and I always tell them, listen, operational solution maybe is better than a technological solution. Okay, so it is very important that nobody knows where you are, but they can know where you are not only detecting you. You know, we're talking about intelligence. I think, we have people here that are much better experts than I am in those fields. But I know that we will see covert communications in a close future. Okay.
Thank you so much. Coffee break time, so we can continue with ask questions in this environment, more relaxing. So thank you so much to our speakers.